Picture a cosmic monster so powerful it can shred entire stars like they're made of paper. A force so immense, not even light can escape its grasp. This isn't science fiction. It's the reality of supermassive black holes, the universe's most enigmatic and terrifying giants. Lurking at the hearts of galaxies, these invisible beasts shape the cosmos in ways we're only beginning to understand. And what we've discovered so far will bend your mind. Some are so vast they could swallow our solar system whole without a second thought. Others spin at nearly the speed of light, warping space and time around them like a cosmic whirlpool. But how do these titans grow so unimaginably large? What happens when they collide, and could one of them ever threaten our corner of the universe? Think about this for a moment. The largest black hole we've found weighs in at a staggering 66 billion times the mass of our Sun. To put that into perspective, if this black hole were placed in our solar system, its event horizon, the point of no return, would stretch farther than the orbit of Pluto. That's not just big, that's universe-altering, and yet, for all their destructive power, supermassive black holes might also be the architects of life itself. Their colossal energies can spark the birth of new stars, forge the elements that make up our bodies, and even dictate the fate of entire galaxies. It's a paradox of creation and destruction playing out on the grandest scale imaginable. Over the next few minutes, we're venturing into the heart of darkness to uncover 30 astonishing facts about these cosmic leviathans. You'll learn how astronomers detect something that emits no light, why some black holes blast jets of matter millions of light years into space, and what happens when two of these monsters merge in a collision that shakes the fabric of space-time. This isn't just a journey through the extremes of physics, it's a glimpse into the forces that built the universe as we know it. So buckle up, we're about to dive into the abyss, and what we find there will leave you in awe. Hidden in the depths of space, roughly 10 billion light-years from Earth, lurks a black hole so colossal it defies comprehension. Meet Ton 618, the undisputed heavyweight champion of the known universe. This cosmic titan tips the scales at 66 billion times the mass of our Sun, making even the supermassive black hole at the Milky Way's center look like a mere pebble in comparison. Discovered in the late 1950s as part of a quasar survey, Ton 618 wasn't immediately recognized for what it truly was. At first, astronomers saw only an unusually bright spot in the constellation Canes Venatici. But as technology advanced, the terrifying truth came into focus. That brilliance wasn't just a distant star. It was the glow of an accretion disk, a swirling vortex of superheated gas and debris orbiting a black hole so vast it could swallow our entire solar system without a burp. To grasp the sheer scale of this monster, picture Pluto's orbit around the Sun. Now imagine a sphere of pure darkness stretching beyond it. That's Ton 618's event horizon, the boundary where gravity becomes so strong even light surrenders. But here's what's truly mind-bending. While the black hole itself is invisible, its accretion disk shines with the luminosity of 140 trillion suns. That's brighter than all the stars in the Milky Way combined, a beacon visible across the universe. Scientists believe this staggering energy comes from matter spiraling into the abyss at nearly light speed, heating up to millions of degrees before vanishing forever. It's like watching a cosmic hurricane where the winds scream across space at unimaginable velocities, fueled by the hunger of an insatiable void. What makes Ton 618 even more fascinating is its age. We're seeing it as it existed 10 billion years ago, a time when the universe was barely a third of its current age. How did a black hole grow so enormous so quickly? That question keeps astronomers awake at night. Some theories suggest it gorged itself during the chaotic early universe, where dense gas clouds and frequent galaxy collisions provided an all-you-can-eat buffet. Others speculate it might be the result of multiple black holes merging over eons, each collision adding to its incomprehensible mass. One thing's certain, Ton 618 challenges everything we thought we knew about how these cosmic giants form. And somewhere out there, even larger black holes might be waiting to be discovered, lurking in the darkness beyond our current telescope's reach. How do these cosmic behemoths come into existence? The birth of supermassive black holes is one of astronomy's greatest puzzles, with scientists piecing together clues like detectives solving an ancient mystery. One leading theory suggests these monsters grew from smaller seeds, stellar mass black holes left behind after massive stars collapsed. Over billions of years, these seeds gorged on surrounding gas, dust, and even other black holes, bulking up through countless mergers until they reached incomprehensible sizes. Imagine a snowball rolling downhill, gathering more mass with every revolution except in space. That snowball becomes an all-consuming void capable of bending galaxies to its will. But there's a problem with this gradual growth theory when we look at black holes like Ton 618. How could something so massive exist when the universe was so young? This has led scientists to consider a far more dramatic origin story: direct collapse. In the early universe, before stars had fully formed, enormous clouds of pristine gas may have collapsed under their own weight, skipping the star phase entirely and plunging straight into black hole formation. These direct collapse black holes could have been born with masses thousands of times greater than our Sun, giving them a head start in the race to become supermassive. Picture a cosmic shortcut where, instead of building up brick by brick, the universe constructed skyscrapers in a single, breathtaking instant. Dark matter might be pulling the strings behind the scenes. This invisible cosmic scaffolding could have created dense pockets of matter, acting like invisible hands molding the early universe and funneling gas into these growing gravitational traps. Some simulations suggest dark matter halos, vast, ghostly spheres surrounding young galaxies, may have provided the perfect nurseries for supermassive black holes to grow at impossible speeds. Yet for all these theories, mysteries remain. Why do we find these giants in some galaxies but not others? How did they shape the cosmic web we see today? Each discovery peels back another layer of this enigma, revealing just how little we truly understand about the forces that forged our universe. Standing at the edge of a black hole's event horizon is like approaching the ultimate cosmic boundary, a one-way exit from our universe where the laws of physics as we know them cease to exist. Take Sagittarius, a star, the supermassive black hole at the center of our Milky Way. Its event horizon stretches about 12 million miles across, roughly 17 times the Sun's diameter. That might sound enormous, but in the grand hierarchy of black holes, it's practically modest. Now compare that to Ton 618, where the event horizon balloons to a diameter larger than Pluto's entire orbit. If you replaced our Sun with this monster, every planet out to Pluto would vanish inside its pitch-black sphere, leaving no trace behind. Crossing the event horizon isn't like stepping over a visible line. It's an invisible threshold where gravity becomes inescapable. But long before you reached it, another gruesome fate would await: spaghettification. Picture this as you fall feet first toward a black hole. The gravitational pull on your feet grows exponentially stronger than on your head. This tidal force stretches you like taffy, compressing your sides while lengthening your body into a thin, noodle-like strand. Even a sturdy spacecraft wouldn't spare you. The difference in gravity between just a few feet would warp its metal like putty. For smaller black holes, this process happens violently and quickly. But with supermassive ones, the immense size means their gravitational pull increases more gradually. You might actually cross the event horizon before being torn apart, a small mercy in an otherwise horrifying scenario. The chilling reality is that the event horizon isn't just a physical boundary, it's a time warp. From an outsider's perspective, you'd appear to freeze at the edge, your image reddening and dimming as light struggles to escape. But for you, time would rush forward, the universe outside accelerating in a blur as you plunge toward the singularity. It's a cosmic hall of mirrors where space and time trade roles, and all paths lead inward to an unknowable fate. Gravity doesn't just bend space around black holes, it twists time itself into a surreal, almost dreamlike state. Imagine standing near the edge of a supermassive black hole's event horizon, watching the universe outside accelerate like a fast-forwarded film. Here, time slows down so dramatically that what feels like an hour to you could mean decades or even centuries passing for everyone else. This isn't just theoretical. Einstein's theory of relativity predicted this time dilation effect over a century ago, and we've actually observed it happening near cosmic monsters like Sagittarius, a star. Clocks on GPS satellites, for instance, tick slightly faster than those on Earth because they're farther from our planet's gravitational pull, but near a black hole. That effect becomes extreme, warping time to an almost unimaginable degree. The movie Interstellar gave us a visceral glimpse of this phenomenon. Remember the scene where the crew lands on Miller's planet, orbiting Gargantua, a fictional supermassive black hole. For every hour they spend on that watery world, 7 years pass back on Earth. While the numbers were exaggerated for dramatic effect, the science behind it was shockingly real. Black holes spin so rapidly that they drag space-time along with them, creating a whirlpool effect where time itself becomes fluid. The closer you get, the more you're riding this cosmic carousel, moving through time at a different pace than the rest of the universe. But here's where it gets even stranger. If you could hover just outside a black hole's event horizon, say, in a hypothetical indestructible spacecraft, and watch someone fall in, you'd see something bizarre. Their descent would appear to slow down, freezing at the edge as light struggles to escape the gravitational pull. To you, they'd never actually crossed. But from their perspective, time would feel normal as they plunged inward, witnessing the universe outside speed up in a dizzying blur. It's a paradox that still puzzles physicists, two equally real experiences of time playing out simultaneously from different vantage points. This time warping effect isn't just a cool thought experiment, it has real consequences for how we observe black holes. When astronomers study quasars, the incredibly bright disks around supermassive black holes, they're actually seeing light that's been stretched and slowed by these gravitational monsters. The light we detect today may have been emitted billions of years ago, but from the quasar's perspective, time near the black hole passed far more slowly. It's like peering into a cosmic funhouse mirror where the universe's clock ticks at wildly different rates depending on where you're standing. And if humans ever venture near one of these giants, time dilation could turn interstellar travel into a one-way trip to the future, leaving everyone you've ever known long gone by the time you return. Quasars are the universe's ultimate powerhouses, supermassive black holes turned up to 11. These brilliant beacons shine with the light of 1 trillion suns, outshining entire galaxies from the darkest corners of space. At their core lies a ravenous black hole, but unlike their dormant cousins, quasars are actively feasting on cosmic material. As gas, dust, and even whole stars spiral into the abyss, friction heats this matter to unimaginable temperatures, creating a swirling disk of plasma that glows white-hot. The energy released is so intense it can be seen clear across the observable universe, making quasars some of the most distant and oldest objects we've ever detected. These cosmic lighthouses do more than just dazzle. They serve as vital markers for astronomers mapping the vast structure of the cosmos. Because quasars are so bright and located so far away, their light passes through countless galaxies and gas clouds on its journey to Earth. Each time this light interacts with matter, it leaves a unique fingerprint absorption lines in the spectrum that reveal the composition and movement of everything it encountered. It's like shining a flashlight through fog and studying the shadows to understand what's hidden within. Thanks to quasars, we've charted the large-scale web of galaxies and even discovered massive reservoirs of intergalactic gas that would otherwise be invisible. The most astonishing quasars are also time machines. When we observe one 10 billion light-years away, we're seeing it as it existed 10 billion years ago, a snapshot of the early universe. Many of these ancient quasars are far more energetic than their modern counterparts, suggesting supermassive black holes were even more voracious in the cosmos' youth. Some blast jets of charged particles at nearly light speed, stretching hundreds of thousands of light-years into space. These jets can sculpt entire galaxies, triggering or suppressing star formation with their sheer force. It's a reminder that black holes aren't just destroyers, they're cosmic architects, shaping the universe on the grandest scales imaginable. Yet for all their brilliance, quasars have an expiration date. As black holes consume the available fuel in their galaxies, their dazzling accretion disks fade, leaving behind quieter giants like the one at the Milky Way's core. That's why most quasars live in the distant universe. They're relics of a more chaotic, energetic era. But their legacy endures in the galaxies they helped shape and in the light that still travels across space, carrying secrets from the dawn of time. Deep in the cosmic shadows lurks an invisible force that makes up 85% of all matter in the universe: dark matter. This mysterious substance doesn't emit, absorb, or reflect light, yet its gravitational pull shapes galaxies and holds them together. Now, scientists are uncovering tantalizing clues that dark matter might play a starring role in the lives of supermassive black holes. Some theories suggest these invisible particles could be the hidden fuel driving black holes' monstrous appetites, while others propose black holes might act as cosmic anchors, trapping dark matter in their gravitational grip and shaping its distribution across the universe. One compelling idea centers on dark matter halos, vast, invisible spheres of this enigmatic material that envelop galaxies like ghostly cocoons. These halos might funnel ordinary matter toward galactic centers, feeding black holes in a relentless cosmic conveyor belt. Picture a river of dark matter guiding gas and stars into the waiting maw of a supermassive black hole, a silent puppeteer orchestrating the chaos. Simulations show that in the early universe, dark matter's gravitational scaffolding could have accelerated black hole growth, helping them reach staggering sizes faster than previously thought possible. It's as if dark matter handed these cosmic giants a cheat code to bypass normal growth limits. Then there's the spike hypothesis. Near a supermassive black hole's event horizon, dark matter particles might become densely packed, forming a steep gradient of increasing concentration like snow piling up against a fence during a blizzard. This dark matter spike could generate intense gravitational waves when black holes merge, leaving subtle fingerprints in the ripples of space-time. Recent observations from gravitational wave detectors hint at anomalies that might align with this theory, though the evidence remains elusive. But the plot thickens. Some physicists speculate that certain types of dark matter could decay or collide near black holes, producing detectable signals like gamma rays or neutrinos. Others wonder if dark matter itself might collapse into miniature black holes, seeding the growth of their supermassive counterparts. The possibilities are dizzying, and the answers remain just out of reach. With next-generation telescopes and particle detectors, scientists are closer than ever to unraveling this cosmic conspiracy, one that could rewrite our understanding of how the universe's largest structures evolved. What's clear is that the relationship between dark matter and supermassive black holes is far more intricate than we imagined. Whether as a hidden fuel source, a gravitational sculptor, or something even stranger, dark matter seems inextricably linked to these cosmic monsters. And as researchers peel back the layers of this mystery, they're confronting an even deeper question. Could solving the dark matter enigma finally reveal why black holes and galaxies themselves exist as they do? The hunt for answers is on, and the implications could shake astrophysics to its core. Supermassive black holes aren't just passive inhabitants of galaxies, they're active sculptors, shaping their cosmic neighborhoods with invisible hands. Take the way these giants fire colossal jets of charged particles at near light speed, stretching hundreds of thousands of light years into space. These aren't random eruptions, they're precision tools. When a black hole's jets slam into surrounding gas clouds, they can heat the material so intensely that it prevents new stars from forming. It's like a cosmic thermostat, with the black hole dialing star formation up or down based on its appetite. Some galaxies become stellar nurseries bursting with young stars, while others, like massive ellipticals, turn into quiet graveyards where star birth has all but ceased. The difference often comes down to whether their central black hole is actively feeding or lying dormant, but the relationship goes deeper. Galaxies and their black holes grow in lockstep, a cosmic dance tracked by the tight correlation between a galaxy's stellar mass and its black hole size. This isn't coincidence, it's evidence of a feedback loop spanning billions of years. When a black hole feasts, the energy released pushes back against incoming gas, preventing runaway growth. Too little feedback, and the galaxy would form stars uncontrollably, exhausting its fuel. Too much, and star formation shuts down entirely, leaving a galaxy red and dead. The Milky Way sits in a sweet spot, with Sagittarius, a star, occasionally snacking on gas clouds, but mostly leaving our spiral arms to birth new stars at a gentle pace. Then there are the extreme cases, like quasars in the early universe. Their ferocious energy output didn't just regulate star formation, it likely blew entire galaxies apart, ejecting gas needed for future stars into the void. Astronomers have found quasar fossils, galaxies where star formation halted abruptly, their gas reservoirs emptied by black hole winds. It's a reminder that these cosmic titans don't just live in galaxies, they dominate them, with the power to create or destroy on a scale we're only beginning to comprehend. Yet in a twist of cosmic irony, the same forces that suppress star formation might also seed future generations of stars. Black hole jets can compress distant gas clouds as they rampage through a galaxy, triggering new star birth far from the chaos at the center. It's a cycle of destruction and creation playing out over eons, with supermassive black holes as both architects and wrecking balls, proof that even in the darkest corners of space, balance emerges from chaos. Somewhere in the distant cosmos, a black hole is eating the equivalent of our sun every single day. Meet J2157, the universe's most voracious eater, a supermassive black hole so insatiable it's rewriting the rules of cosmic consumption. Discovered in 2018, this monster boasts 34 billion times the mass of our sun and grows at a rate that defies all expectations. If our Milky Way's central black hole, Sagittarius, a star, were a pebble, J2157 would be a mountain, and it's still piling on mass at an astonishing pace. What makes this black hole truly exceptional isn't just its size, but its appetite. While most supermassive black holes nibble on gas clouds or the occasional star, J2157 is at an all-you-can-eat buffet, swallowing the mass of a sun's worth of material daily. That's like devouring Earth's entire Amazon rainforest every 24 hours. The energy released from this feeding frenzy makes its accretion disk glow hotter than thousands of galaxies combined, shining 7,000 times brighter than all the stars in the Milky Way. Astronomers first spotted it because of this outrageous luminosity, a beacon visible halfway across the observable universe. But here's the puzzle: according to current models, black holes shouldn't be able to grow this fast. There's a theoretical limit called the Eddington limit, which predicts how quickly a black hole can consume matter before radiation pressure from its own heat pushes material away. Imagine trying to drink from a fire hose. Eventually, the force of the water would knock you backward. J2157 isn't just sipping, it's gulping down matter at rates that should be impossible, suggesting our understanding of black hole physics might be missing a critical piece. One leading theory: this black hole might have hit the cosmic jackpot, a perfect storm of conditions where gas flows in at just the right angles, bypassing the usual bottlenecks. Or perhaps it's the result of a recent merger where two giant black holes collided, creating a single, even hungrier offspring. Whatever the reason, J2157 is a living laboratory, showing us that the universe's most extreme objects still have secrets to reveal. And as astronomers study its ravenous behavior, they're uncovering clues about how black holes shaped the cosmos in its earliest, most chaotic days. When two supermassive black holes spiral toward each other, they don't just collide, they shake the universe. These cosmic mergers send gravitational waves rippling through space-time like seismic tremors from an earthquake, warping the very fabric of reality. In 2015, scientists at LIGO, the Laser Interferometer Gravitational Wave Observatory, made history by detecting these ripples for the first time, proving Einstein's century-old prediction correct. But the black holes LIGO spotted were mere minnows compared to the true giants lurking in galactic centers. When supermassive black holes merge, they unleash gravitational waves with wavelengths so vast they could span entire solar systems, carrying more energy than all the stars in the observable universe combined. LIGO current detectors are tuned to catch the high-pitched chirps of stellar mass black holes objects weighing tens of times our Sun. But to hear the deep, bass notes of supermassive mergers, we need an entirely new kind of observatory. Enter pulsar timing arrays, networks of ultra-precise cosmic clocks scattered across the galaxy. These rapidly spinning neutron stars emit beams of radio waves with metronome-like regularity. As gravitational waves pass through space, they stretch and compress the distances between pulsars and Earth, creating telltale irregularities in the rhythm of their pulses. It's like listening to an orchestra where some instruments gradually fall out of sync, revealing the universe's deepest vibrations. The next leap comes with space-based detectors like LISA, the Laser Interferometer Space Antenna. Slated for launch in the 2030s, this trio of spacecraft will form a triangular observatory millions of miles across, sensitive to low-frequency waves from black holes weighing millions or even billions of solar masses. Imagine holding a telescope not to the sky, but to space-time itself, tuning into the echoes of collisions that occurred when the universe was young. These waves could reveal how supermassive black holes grew so large so quickly, whether they're born from direct collapse or built through countless mergers, and even how dark matter influences their dance. Already, pulsar timing arrays are hinting at a possible background hum, a chorus of gravitational waves from countless supermassive black hole pairs circling each other across the cosmos. If confirmed, it would be like standing near a shoreline and hearing the roar of every ocean wave rolled into one. Future detections might catch individual mergers in action, watching as two black holes spiral inward over centuries before finally crashing together in an event so violent it briefly outshines all the stars in the universe. These collisions don't just create new black holes, they can kick them clear out of their host galaxies at speeds topping 3 million miles per hour, sending them careering through intergalactic space like cosmic cannonballs. Yet the most profound revelation might still be ahead. Some theories suggest certain gravitational wave signatures could betray hidden dimensions or reveal quantum effects near black hole event horizons, clues to reconciling Einstein's relativity with quantum mechanics. Every ripple in space-time carries information about the universe's most extreme environments, places where gravity becomes so strong it twists the rules of physics beyond recognition. And as our detectors grow more sensitive, we're not just listening to black holes, we're learning to decode the symphony of the cosmos itself. Traveling back to the universe's infancy, just 690 million years after the Big Bang, we find Euler's J1342, a black hole that shouldn't exist. This ancient behemoth, weighing in at 1 billion times the mass of our Sun, poses a cosmic riddle. How could something so massive form so quickly? The early universe was a chaotic, rapidly expanding place where matter hadn't yet clumped into the galaxies we recognize today. Conventional models suggest black holes grow slowly, feasting on gas and merging over eons. But Euler's J1342 defies those rules, appearing fully formed when the cosmos was less than 5% of its current age. It's like discovering a skyscraper in the middle of a primordial jungle, a structure that, by all accounts, had no time to be built. This black hole's existence forces scientists to reconsider the cosmic dawn, the period when the first stars and galaxies flickered to life. One leading theory suggests Euler's J1342 grew from a seed black hole far larger than those left by collapsing stars. These seeds might have formed from the direct collapse of massive gas clouds, skipping the star phase entirely and collapsing straight into a black hole weighing tens of thousands of solar masses. Picture a cosmic shortcut where gravity worked overtime to compress matter into a ready-made monster. Another possibility: the early universe's dense environment allowed black holes to gorge on gas at unprecedented rates, growing faster than anything we see today. Yet the real enigma isn't just its size, it's the light it emits. Euler's J1342 is a quasar. It's a crescent disk blazing with the brightness of a trillion suns. That brilliance is our only window into this distant epoch, a flashlight beam piercing the fog of the early cosmos. By studying its light, astronomers have glimpsed the conditions of the universe's first chapters, a time when space was filled with a murky hydrogen haze before the first stars fully cleared the cosmic fog. This black hole's radiation might even hold clues to how that transition occurred, its ultraviolet photons shredding nearby hydrogen atoms and carving bubbles of transparency in the primordial darkness. What's most startling is that Euler's J1342 likely wasn't alone. If one supermassive black hole existed so early, others must have two, perhaps even larger ones, still undiscovered. Their presence rewrites the timeline of cosmic history, suggesting black holes didn't just grow alongside galaxies but possibly predated them, serving as gravitational anchors around which the first stars and galaxies assembled. It's a humbling thought. These invisible giants might have been the universe's first architects, their immense gravity sculpting the cosmos long before the Milky Way's spiral arms took shape. And as telescopes probe deeper into space and further back in time, each discovery brings us closer to understanding how darkness shaped the dawn of light. Some black holes play the ultimate cosmic vampire, slowly draining the life from their stellar companions in a relentless feeding frenzy. Among these celestial predators, Cygnus X1 stands out, a black hole 12 times the mass of our Sun, locked in a deadly dance with a blue supergiant star. Every 5.5 days, the black hole swings perilously close to its companion, stretching the star with tidal forces powerful enough to rip gas from its surface. This stolen matter spirals inward, forming an accretion disk so hot it glows in X-rays visible across the galaxy. Discovered in 1964, Cygnus X1 became the first object widely accepted as a black hole, revolutionizing our understanding of these invisible monsters. The beauty of systems like this lies in what they reveal about black hole physics. By measuring the companion star's wobble as the black hole tugs it through space, astronomers can calculate the unseen predator's mass with astonishing precision. It's like watching someone dance with an invisible partner. Their movements betray the partner's size and strength. Cygnus X1's discovery provided the first concrete evidence that massive stars could collapse into black holes, confirming theories that had seemed like pure speculation. What makes these vampiric black holes even more fascinating is their accretion disks. As stolen gas swirls toward oblivion, friction heats it to millions of degrees, creating a rotating inferno that emits high-energy radiation. Sometimes the disk becomes unstable, ejecting jets of particles at nearly light speed, cosmic blowtorches that can stretch for light years. These outbursts serve as natural laboratories, letting scientists study extreme physics impossible to recreate on Earth. Yet the star isn't just a passive victim. Its powerful stellar winds feed the black hole continuously, even at greater distances, creating a fluctuating relationship where the feeding rate changes over time. Some systems even flip between soft and hard X-ray states as the accretion disk structure shifts, offering clues about how black holes regulate their own growth. While Cygnus X1 will eventually exhaust its stellar meal, its legacy endures, a Rosetta Stone for decoding how black holes interact with their cosmic neighbors, one stolen breath at a time. Silence isn't always what it seems, especially in space. Take the Perseus cluster, a galaxy group 250 million light-years away with a supermassive black hole at its heart. While we often think of space as soundless, NASA Chandra X-ray Observatory revealed something astonishing. This black hole has been singing a single haunting note for billions of years. It's the deepest sound ever detected in the universe, a B-flat 57 octaves below middle C, a frequency so low human ears couldn't possibly hear it. But by translating the black hole's pressure waves into audible sound, scientists gave voice to the cosmos in a way that's both eerie and revolutionary. How does a black hole, an object so dense even light can't escape, produce sound? The secret lies in the superheated gas surrounding it. As material spirals toward the event horizon, the black hole's immense gravity creates ripples in this gas, sending out pressure waves like sound waves through water. These waves travel outward, pushing and pulling on the cluster's plasma in rhythmic pulses. While space is mostly a vacuum where sound can't travel normally, the dense gas in Perseus acts like a medium, allowing these waves to propagate across hundreds of thousands of light-years. It's less like a traditional sound and more like seismic tremors reverberating through a cosmic ocean. The process of converting these waves into something audible is a feat of astronomical imagination. Researchers took X-ray data mapping the gas density variations around Perseus's black hole, then scaled the frequencies up by quadrillions of times to shift them into the human hearing range. What emerged was a ghostly, almost meditative hum, a single sustained tone that sounds more like the groan of a distant ship than anything musical. Yet this note holds scientific gold. By studying its pitch and amplitude, astronomers can map the distribution and temperature of the cluster's gas with unprecedented precision, revealing how black holes heat their surroundings and prevent runaway star formation. But here's what's truly mind-bending. That note has been resonating continuously for roughly 2.5 billion years. If we could hear it in its original form, sans scaling, one vibration would take 16 million years to complete. Imagine a sound so slow its waves are separated by geological timescales, a bass line written into the fabric of the cosmos itself. Other black holes have since joined this cosmic choir, including M87's famous jet, which produces a rising tone like an otherworldly kettle whistle when sonified. Listening to these sounds isn't just eerie, it's reshaping how we understand the dynamic interplay between black holes and their environments, proving even the darkest corners of the universe vibrate with hidden rhythms. This sonic exploration has practical implications beyond the cool factor. By analyzing these pressure waves, scientists can measure properties like gas density and black hole mass indirectly. It's similar to how geologists study earthquakes, except instead of ground vibrations, they're tracking space-time ripples to decode the universe's largest structures. And as telescopes gather more data, we're discovering that black holes don't just consume and destroy. They resonate, sending vibrations through the cosmos that echo for eons. These sounds are more than cosmic curiosities. They're the heartbeat of the universe's darkest giants, a reminder that even in the void, there's music. Black holes aren't just engines of destruction, they're cosmic recyclers, scattering the ingredients for life across the universe. Picture this: as matter spirals toward a black hole's event horizon, some of it gets channeled into powerful jets shooting outward at nearly light speed. These jets act like intergalactic sprinklers, spraying heavy elements forged in stellar furnaces and supernova far into the voids between galaxies. Without this process, the universe would lack the carbon, oxygen, iron, and other essential elements that make up planets, oceans, and even our own bodies. Take the black hole at the center of galaxy M87, famous for its colossal jet stretching 5,000 light-years into space. Analysis reveals this jet isn't just raw energy, it's packed with atoms heavier than hydrogen and helium, the building blocks of rocky worlds. When these jets slam into surrounding gas clouds, they trigger shock waves that compress the material, simultaneously dispersing heavy elements and jump-starting new star formation. It's a celestial cycle where death births life, with black holes serving as the catalysts. This recycling has profound implications for life as we know it. The iron in our blood, the calcium in our bones, even the gold in jewelry, all were forged in the hearts of dying stars and scattered by processes like black hole jets. Some theories suggest our solar system might owe its existence to such an event. A nearby black hole's outburst billions of years ago could have compressed a gas cloud just enough to trigger the collapse that formed the sun and planets. Without these violent cosmic events, Earth might never have accumulated the rich diversity of elements necessary for life to emerge. Yet the recycling doesn't stop at our galaxy. Black hole jets can propel material clear out of their host galaxies, seeding intergalactic space with precious atoms. Over billions of years, these wandering elements become incorporated into new galaxies, enriching them with the raw materials for future solar systems. It's a slow-motion dance of creation spanning cosmic epochs, where today's black hole feast becomes tomorrow's starlight, and perhaps the foundation for life yet to come. Einstein's equations contain a cosmic loophole that still baffles physicists today: the possibility of naked singularities. Unlike typical black holes shrouded by event horizons, these hypothetical monsters would expose their infinitely dense cores to the universe, turning physics as we know it inside out. The concept emerged from mathematical solutions to general relativity, showing that under certain conditions, like a black hole spinning at the absolute limit, its event horizon might vanish, leaving the singularity fully visible. It's as if the universe's ultimate "no trespassing" sign suddenly disappeared, exposing a realm where gravity becomes infinite and space-time itself fractures. Why does this matter? Event horizons act as cosmic sensors, hiding the breakdown of physical laws from view. Remove that curtain and the paradoxes become inescapable. At a naked singularity, time could loop backward, cause and effect might unravel, and predictability, the cornerstone of science, would crumble. Imagine throwing a baseball toward such an anomaly. Near a regular black hole, the ball crosses the horizon and disappears forever. But near a naked singularity, the same ball could reappear in multiple places at once, travel faster than light, or even emerge before you threw it, violating fundamental laws like a glitch in reality's code. The hunt for these anomalies isn't just academic. Some theorists propose that the Big Bang itself might have been a naked singularity, a moment when all physical laws temporarily broke down. Others speculate that colliding black holes could momentarily strip each other's horizons during merger, creating short-lived naked singularities that imprint bizarre signatures in gravitational waves. There's even a fringe idea that advanced civilizations might engineer naked singularities as infinite energy sources or space-time gateways, though that ventures deep into science fiction territory. Yet most physicists believe nature abhors naked singularities, preventing their formation through mechanisms we don't yet understand. This cosmic censorship hypothesis proposed by Roger Penrose suggests unknown physics always cloaks singularities behind horizons. The debate rages because Einstein's equations don't forbid naked singularities outright, they merely make them improbable. If one were discovered, it would force a rewrite of general relativity, quantum mechanics, or both, a scientific revolution waiting in the depths of space. For now, these mathematical phantoms remain tantalizingly out of reach, reminding us that even our best theories have unexplored edges where reality might bend in unimaginable ways. That glowing orange ring you've seen in headlines isn't just an artist's rendition. It's the first direct visual evidence of a black hole's shadow, captured by the Event Horizon Telescope back in 2019. The subject of that groundbreaking image, M87 star, a supermassive black hole 55 million light-years away with a mass of 6.5 billion suns. But here's what most people miss: that iconic donut isn't the black hole itself. It's the warped silhouette of the event horizon, backlit by an inferno of superheated gas swirling at nearly light speed. To understand how this cosmic portrait came to be, picture standing behind a campfire on a foggy night. The flames illuminate the mist around them, creating a bright halo, but any object placed in front would cast a dark shadow against that glow. M87 star's shadow works the same way. Its event horizon bends light so severely that photons looping around it create a photon ring, a circle of light surrounding a central darkness 2.5 times wider than the actual event horizon. That's the eerie void we're seeing, a region where spacetime's curvature becomes so extreme it traps even light on endless orbits. Capturing this shadow required stitching together data from 8 radio telescopes across 4 continents, effectively creating an Earth-sized virtual telescope with resolution sharp enough to spot a donut on the moon. Each observatory recorded the faint radio whispers of M87 star's accretion disk, emissions produced by electrons spiraling through magnetic fields at temperatures over 10 billion degrees. Then, supercomputers spent years crunching petabytes of data to reconstruct the image, a process akin to assembling a jigsaw puzzle where half the pieces were missing. Why does this matter beyond the awe factor? That shadow's size and shape are cosmic Rosetta Stones. General relativity predicts black hole shadows should appear nearly circular regardless of viewing angle, and M87 star's perfect ring confirmed Einstein's equations yet again, this time in conditions 1,000,000 times more extreme than previous tests. But subtle deviations in the ring's brightness could hint at even deeper physics, like whether the black hole's spin drags spacetime into a whirlpool-like vortex around it. Future observations aim to capture movies of this shadow, revealing how it wobbles as the black hole consumes matter, a real-time window into gravity's strongest grip. The real triumph isn't just seeing the unseeable, it's what comes next. Already, the HT has turned its gaze toward Sagittarius, a star, our Milky Way's quieter black hole. While closer, its shadow is harder to image because it flickers rapidly as it snacks on passing gas clouds. Cracking that puzzle could reveal why some black holes feast while others starve, and how these hidden giants orchestrate the galaxies they call home. One thing's certain: humanity's first glimpse of a black hole's shadow wasn't an endpoint. It was the opening scene of an entirely new chapter in astrophysics. The cosmos we know, brimming with galaxies, stars, and planets, is just a fleeting chapter in an epic saga stretching trillions of years into the future. And in that unimaginably distant era, supermassive black holes may become the universe's final rulers. Picture a time so far ahead that all stars have burned out, galaxies have evaporated, and even the protons making up matter itself begin to disintegrate. Against this desolate backdrop, black holes would stand alone as the last surviving structures, their immense gravity defying the universe's slow fade into darkness. This grim timeline is known as the black hole era, a phase beginning around 10 to the power of 40 years from now. By this point, stellar remnants like white dwarfs and neutron stars will have cooled into cold, lifeless husks or decayed entirely. Even the once vast supermassive black holes, having feasted on galaxies for eons, will begin shedding mass through a bizarre quantum process called Hawking radiation. Imagine a black hole not as a cosmic vacuum, but as a leaky bucket slowly dripping particles into space. Over mind-boggling timescales, this trickle becomes a flood, causing even the mightiest black holes to shrink and eventually vanish in a final burst of radiation. But before that in-game, these giants will shape the universe in ways we can scarcely comprehend. As galaxies disperse and stars vanish, black holes will gravitationally dominate their regions, capturing any remaining wandering objects. Some models suggest they'll form vast, isolated kingdoms, each black hole presiding over a dark sphere of influence where nothing escapes. In rare cases, pairs of these titans might still merge, sending gravitational waves rippling through an otherwise silent cosmos long after light itself has dimmed. The ultimate fate hinges on whether protons, the building blocks of atoms, are truly stable. If proton decay exists, as many physicists suspect, even black holes will eventually find themselves with nothing left to consume. Matter itself will dissolve into subatomic particles, leaving a universe where black holes are the only structures complex enough to be called objects. Yet even they won't last forever. The smaller a black hole becomes through Hawking radiation, the faster it evaporates, leading to a crescendo where the last black holes vanish in bursts of high-energy photons. What remains is a universe so bleak it makes today's deepest void seem vibrant, an expanse of near-perfect darkness where only the faintest particles and radiation wander. Time stretches meaningless without events to mark its passage, and space itself may continue expanding until even the memory of structure fades entirely. Yet in this cosmic twilight, black holes will have written the final chapter, their immense gravity the last force shaping reality before the curtain falls on everything. It's a humbling thought. The same monsters that terrify us today might one day be the universe's last keepers of order before the long descent into entropy's silence. When two supermassive black holes collide, the aftermath isn't just a bigger black hole. It's a cosmic slingshot capable of launching the merged monster clear out of its galaxy. These gravitational recoils, or black hole kicks, occur when the violent merger sends ripples through space-time so unevenly that the newly formed black hole gets rocketed in the opposite direction at speeds up to 3 million miles per hour. That's fast enough to travel from Earth to the Moon in under 5 minutes, a velocity so extreme it can overcome even a galaxy's gravitational grip. Take CD42, a bizarre object 7 billion light-years away that looks like a quasar caught mid-ejection. Hubble images show two distinct light sources racing apart, one likely the recoiling black hole, the other its abandoned host galaxy. Analysis revealed the black hole zooming away at nearly 5 million miles per hour, trailing a stream of young stars torn loose during its chaotic escape. It's as if the universe's most destructive divorce played out on a galactic scale, with the black hole as the runaway spouse taking part of the stellar furniture. The physics behind these kicks is even wilder. When two black holes spiral toward merger, they emit gravitational waves more intensely in one direction than another, like a garden hose whipping around unpredictably. This lopsided radiation carries away momentum, creating a recoil effect similar to a gun's kickback. The final kick velocity depends on the black hole's spins and orbits. If they're misaligned or rotating rapidly, the merged black hole can get a staggering push. Simulations show some mergers might even produce kicks strong enough to send black holes flying into intergalactic space forever. Orphan giants wandering the cosmic voids between galaxies. Yet not all kicked black holes make a clean break. Some, like SDSS J0927, are caught in a gravitational tug of war, recoiling from their galactic cores but still tethered by faint tendrils of stars. These wandering black holes create bizarre hybrid systems where the galaxy's center of mass no longer aligns with its visible core. Astronomers suspect our own Milky Way might host such a wanderer, a mid-sized black hole called G-Surs 13e, drifting unusually far from Sagittarius, a star. If confirmed, it could be evidence of an ancient merger that didn't quite set its black hole free. The implications stretch far beyond cosmic curiosities. Ejected black holes leave behind galaxies with disrupted cores, potentially altering star formation for eons. Some theories suggest these kicks could explain naked quasars, bright accretion disks untethered from visible host galaxies. Others speculate that the loneliest supermassive black holes, cast adrift in intergalactic space, might accumulate dark matter halos dense enough to form exotic, black hole galaxies, invisible islands of pure gravity roaming the cosmos. Each discovery of a recoiling black hole peels back another layer of the violent, dynamic processes shaping our universe, proving even the mightiest objects aren't immune to getting kicked out of the house. One of the most radical ideas in modern physics suggests that everything we experience, every galaxy, star, and even our own thoughts, might be nothing more than a cosmic projection. This is the holographic principle, a theory that ties the mind-bending nature of black holes directly to the fundamental structure of reality. Imagine peeling the label off a soda bottle, the shiny holographic sticker that changes images when you tilt it. At first glance, it's a three-dimensional scene, but look closer and you'll realize all that complexity is encoded on a flat, two-dimensional surface. The holographic principle proposes our universe works the same way that the three-dimensional reality we perceive could be a projection of information stored in two dimensions on the edge of a black hole's event horizon. This isn't just philosophical speculation. The math behind black hole thermodynamics hints at something astonishing. The maximum amount of information a region of space can contain doesn't depend on its volume, but on the area of its boundary. It's as if the universe is telling us that everything happening inside a black hole, or by extension, any region of space, is completely described by information painted on its surface. Think of it like watching a movie. The three-dimensional action you see on screen is actually encoded in flat, two-dimensional pixels. In the same way, the holographic principle suggests that black holes might be the universe's ultimate storage devices, with their event horizons acting like cosmic hard drives encoding the information of everything that falls inside. Where does this idea come from? It started with a paradox about black holes and information. When matter gets swallowed by one, it seemingly vanishes forever, taking its information with it. But quantum mechanics insists information can never truly be destroyed. The holographic principle resolves this by suggesting the information isn't lost. It's imprinted on the event horizon in vanishingly tiny bits called Planck areas, each just 1/10 trillionth of a centimeter across. Every particle, every force, every moment of history that falls into the black hole leaves a fingerprint on this two-dimensional surface, like ripples frozen in time. What's even stranger is that this might apply to the entire universe. Some theories propose that our whole cosmos could be a holographic projection from a two-dimensional surface at the edge of space-time, a boundary we can't see or interact with. Black holes, with their clear boundaries and extreme physics, might be the key to unlocking this mystery. Experiments with gravitational wave detectors and quantum computers are now searching for signatures of holography, subtle glitches in reality that could reveal we're living in a projected universe. If the holographic principle holds true, it would mean that the vast three-dimensional cosmos we see, with its spiraling galaxies and swirling nebulae, is really just a shadow play. The true action is happening on a distant two-dimensional surface we'll never see, with black holes serving as cosmic projectors. It's a humbling thought. The universe's most destructive objects might also be the artists painting our reality into existence, one infinitesimal pixel at a time. The idea of black holes as cosmic shortcuts, tunnels to distant galaxies or even other universes, has fueled science fiction for decades. From Interstellar's breathtaking journey through the wormhole gargantua to Star Trek's convenient plot devices, the notion that these gravitational monsters might be gateways seems irresistible. But is there any scientific basis for this tantalizing possibility? The answer lies in an obscure solution to Einstein's equations called an Einstein-Rosen bridge. a theoretical structure linking two black holes like a hallway between distant points in space. At first glance, the math checks out. General relativity allows for the existence of wormholes, but with a catch: they'd be incredibly unstable. Picture trying to cross a bridge made of soap bubbles. The moment anything touches it, even a single photon of light, the wormhole would collapse instantly, crushed by its own gravitational forces. Keeping it open would require something even more exotic: matter with negative energy density, a substance that defies gravity by pushing space outward rather than pulling inward. This exotic matter isn't just rare, it's never been observed in nature, though quantum mechanics hints that bizarre phenomena like the Casimir effect might produce microscopic amounts under lab conditions. Even if we could stabilize a wormhole, the journey would be unpleasant. The intense tidal forces near a black hole's singularity would stretch anything attempting passage into a stream of atoms, hardly the smooth ride sci-fi promises. Some models suggest rapidly spinning black holes might offer gentler conditions, their rotation creating a donut-shaped singularity with a potentially navigable center. But here's the twist: you'd never actually choose where you exited. Exiting the other side could spit you out anywhere in space or time, with no way to control the destination. Yet the dream persists because the universe keeps surprising us. Recent research into quantum entanglement, where particles remain mysteriously linked across vast distances, has sparked new theories about microscopic wormholes threading through space-time. Some physicists speculate that every black hole might be connected to a white hole, a hypothetical region where matter and energy gush outward. Others imagine advanced civilizations manipulating wormholes with cosmic-scale engineering, though that remains firmly in speculation's realm. The truth is, wormholes captivate us because they embody the ultimate escape, a backdoor through the universe's strictest rules. While today's physics says they're improbable, it doesn't say impossible. And in a cosmos where black holes warp time, shred stars, and hide singularities of infinite density, perhaps the wildest ideas are just waiting for the right equations. At the heart of black hole physics lies a paradox so profound it threatens to unravel our understanding of reality itself, the infamous information paradox. Here's the problem: when Stephen Hawking revealed black holes slowly evaporate through radiation, he also concluded they permanently erase information about anything they swallow. A book tossed into a black hole wouldn't just be unreadable, it would be as if every word, every letter, every atom that composed it never existed in the first place. This clashes violently with quantum mechanics' bedrock principle. Information can never be truly destroyed, only scrambled. It's like claiming you could burn a library to ashes and have no physical trace left of the stories it held, not even in the smoke. For decades, physicists wrestled with this dilemma. If Hawking was right, quantum theory's predictability crumbles. Yet if information somehow escapes black holes, Einstein's general relativity needs rewriting. The stakes couldn't be higher. It's a battle for the soul of physics itself. Enter the firewall hypothesis. One radical solution proposing the event horizon isn't a smooth gateway but a searing wall of energy. Picture approaching what you think is a calm lake, only to hit an invisible sheet of flame. In this scenario, the firewall incinerates anything crossing it, preserving information by converting it into radiation, but at the cost of violating relativity's prediction that falling into a black hole should feel uneventful until it's too late. Another groundbreaking solution leans on the holographic principle, suggesting black holes don't destroy information. They encode it in 2D on their event horizons like cosmic etch-a-sketches. Every particle swallowed leaves a ghostly imprint in Planck-sized pixels on the surface, preserving data in a form we can't yet decode. It's as if the universe stores a backup copy of everything lost inside, just in an alien language we're still learning to read. Recent breakthroughs in string theory and quantum gravity lend weight to this idea, showing how information might leak back out via Hawking radiation. not as random noise but as a scrambled message waiting to be decrypted. The plot thickens with soft hair, a concept suggesting black holes grow faint quantum fuzz low-energy excitations around their horizons that subtly record information. Think of it like a black hole's version of a security camera, capturing fuzzy snapshots of its meals. While these theories differ wildly, they share a thrilling implication. Black holes might be the universe's most sophisticated vaults, not its shredders. Experiments like gravitational wave detectors are now hunting for fingerprints of these exotic solutions, probing whether mergers leave behind information-rich echoes or hidden signatures in spacetime's ripples. What makes this paradox so pivotal isn't just abstract physics, it's a gateway to unifying quantum mechanics and gravity, two frameworks stubbornly resistant to reconciliation. Crack the information puzzle, and we might finally glimpse the theory of everything, hidden all along in the darkest corners of the cosmos. Until then, black holes remain the ultimate cosmic locksmiths, guarding their secrets behind event horizons where even the laws of physics seem to bend. Rising high above the Milky Way's disk like a pair of colossal hourglasses, the Fermi bubbles stretch 50,000 light-years from end to end, nearly half the diameter of our entire galaxy. These gargantuan structures, discovered in 2010 by NASA, a Fermi gamma-ray space telescope, glow faintly in high-energy gamma rays, outlining what scientists believe are the remnants of an ancient cataclysm. And the prime suspect behind this cosmic graffiti, none other than Sagittarius, a star, the supermassive black hole lurking at our galaxy's core. These bubbles aren't just random space fog, they're fossil evidence of a violent outburst that rocked the Milky Way millions of years ago, a tantrum from our black hole so powerful it left scars across intergalactic space. What makes these bubbles so fascinating is what they reveal about black holes' hidden moods. Sagittarius, a star, may seem quiet today, barely nibbling on passing gas clouds, but the Fermi bubbles prove it was once a ferocious beast. Imagine your neighborhood volcano dormant for centuries, then stumbling upon layers of ancient ash, proving it once erupted with 1,000 times Mount Vesuvius's fury. That's the scale we're talking about. When Sagittarius, a star, erupted, it likely blasted jets of charged particles at nearly light speed, punching through the galaxy's gas like cosmic blowtorches. The shockwaves from this explosion heated surrounding material to millions of degrees, creating the bubble's glowing edges we detect today. But here's where it gets even stranger. The bubbles aren't symmetrical. One stretches slightly farther than the other, suggesting the eruption wasn't a clean explosion but more like a messy belch. Some theories propose our black hole might have consumed a particularly hefty gas cloud or even a stray star, triggering an uneven discharge of energy. Others speculate the Milky Way's tilted magnetic fields could have funneled the outburst in lopsided ways. Whatever the cause, these imperfections are cosmic gold for astronomers, offering clues about how black holes interact with their galactic environments over eons. The real magic lies in what the bubbles are made of, not just hot gas, but a soup of high-energy particles called cosmic rays. These subatomic bullets, accelerated by the black hole's eruption, still zip through the bubble's interiors, colliding with cooler gas to produce the gamma rays Fermi detected. It's like finding an ancient battlefield still littered with unexploded ordnance, each gamma ray photon a smoking gun from Sagittarius, a star's past violence. By mapping these emissions, scientists have reconstructed the eruption's timeline, likely a series of outbursts spanning tens of thousands of years, peaking around 2.5 million years ago. That date raises eerie possibilities. Around the same time, Earth's climate shuddered through the Quaternary glaciation, when ice sheets advanced and our ancestors first tamed fire. Could there be a connection? While it's a stretch to claim the black hole caused ice ages, some researchers speculate the bubble's particle bombardment might have subtly influenced our planet's cloud formation or atmospheric chemistry. More importantly, the Fermi bubbles remind us that galactic centers aren't static, they're dynamic engines capable of reshaping entire galaxies. If our relatively quiet black hole could unleash such havoc, imagine the fury lurking in quasars or colliding galaxies. Yet the greatest lesson might be about our own black hole's future. Sagittarius, a star's outburst proves even dormant giants can reawaken, especially as the Milky Way barrels toward a collision with the Andromeda Galaxy in 4 billion years. That cosmic car crash could funnel fresh gas toward our central black hole, potentially triggering new eruptions. The Fermi bubbles stand as both a warning and a promise, a reminder that the universe's most violent forces aren't just out there in distant galaxies. They're right in our own cosmic backyard, sleeping lightly beneath the Milky Way's shimmering stars. Even the mightiest black holes in the universe aren't eternal, and Ton 618, the colossal king weighing 66 billion solar masses, will eventually meet its demise. But this won't be a quick or dramatic end. Over timescales so vast they dwarf the current age of the universe, even this monster will fade away, particle by particle, through a process as subtle as it is inevitable: Hawking radiation. Right now, Ton 618 is far too massive to lose significant energy this way. Hawking radiation works inversely to size. The smaller the black hole, the faster it evaporates. For a titan like Ton 618, the trickle of escaping particles is so feeble it would take around 1 followed by 100 zeros years to fully dissipate. To put that in perspective, if the entire lifespan of our universe so far were compressed into a single second, the time needed for Ton 618 to vanish would stretch longer than all the seconds that have ever passed multiplied by 1 trillion. But let's fast forward to an era when stars have burned out, galaxies have dispersed, and the universe has expanded into a cold, near-empty void. In this distant future, Ton 618 will finally start losing mass at a noticeable rate. As it shrinks, its evaporation accelerates, creating a runaway effect where the last stages unfold in a flash compared to the eons that came before. The final moments would be spectacular, a burst of high-energy radiation as the remaining mass converts entirely into particles, leaving behind nothing but an echo in the cosmic background. Yet before that distant end, Ton 618 might have one last act, a merger. In a universe where galaxies collide and combine, supermassive black holes often spiral together, drawn by gravity until they create an even larger singularity. Given its location in a bright quasar, Ton 618 likely sits at the heart of a massive galaxy, which could one day intersect with another. If it meets a rival supermassive black hole, the resulting collision would unleash gravitational waves powerful enough to ripple across the entire cosmos, distorting spacetime itself. There's another, more exotic possibility. Some theories suggest that in a far future universe dominated by dark energy, black holes might become islands of stability in an otherwise empty expanse. Ton 618 could outlast everything else, serving as a gravitational anchor long after all other structures have been pulled apart by cosmic expansion. It might even become a refuge for any hypothetical far future civilizations, harnessing its immense gravity as an energy source or a time capsule preserving information from a vanished era. But physics at these extremes remains uncertain. Quantum gravity effects, still poorly understood, could rewrite the rules at the very end. Perhaps instead of vanishing in a burst of radiation, Ton 618 leaves behind a remnant, an ultra-dense nugget of spacetime where the laws of physics as we know them break down entirely. Or maybe it births something entirely unexpected, like a wormhole or a bridge to another universe. One thing's certain: Ton 618's fate is tied to the universe's own. Whether it evaporates quietly, merges spectacularly, or outlasts everything else, its story will shape the cosmos until the very end of time. Einstein's theory of relativity gave us more than just equations. It revealed a universe where black holes double as nature's most powerful telescopes. These cosmic monsters don't just consume light, They warp it so dramatically that they act as gravitational lenses, bending and magnifying distant objects like celestial magnifying glasses. Picture a black hole drifting between Earth and a faraway galaxy. Instead of blocking the galaxy from view, the black hole's immense gravity distorts space-time so severely that the galaxy's light curves around it, creating multiple distorted images or even a glowing ring of starlight. Astronomers call these perfect rings Einstein rings, halos of warped light predicted by Einstein in 1936, but not observed until the 1980s when our telescopes finally caught up to his genius. One of the most stunning examples lies in the constellation Fornax, where a massive galaxy cluster bends the light from an even more distant galaxy into a near-perfect luminous circle. This cosmic bullseye, dubbed the molten ring for its fiery appearance, isn't just beautiful, it's a scientific goldmine. Because the lensing effect amplifies the background galaxy's light, astronomers can study details otherwise impossible to see: nascent star clusters, swirling gas clouds, and even hints of dark matter distribution. It's like turning the universe's contrast dial to maximum, revealing faint structures hidden in the cosmic backdrop. But black holes take lensing to extremes. Their sharper gravitational fields can create bizarre optical illusions called Einstein crosses, where a single quasar appears as 4 distinct images around the lensing black hole. In one famous case, a quasar 6 billion light-years away was quadruply imaged by a foreground galaxy's central black hole, forming a cross-shaped pattern that helped astronomers precisely map the black hole's mass. These multiple images aren't just static, they flicker over time as the black hole's gravity subtly shifts the light paths, offering a real-time lab to test relativity's predictions. The true power of black hole lenses lies in their ability to unveil the invisible. When astronomers study distorted images of background galaxies, they can reconstruct the mass distribution of the lensing black hole and its surrounding dark matter halo. It's like using a funhouse mirror to deduce the shape of the mirror itself. In 2021, researchers used this technique to detect an orphaned black hole wandering 7,000 light-years away, its presence betrayed only by the way it briefly magnified a star's light as it passed between the star and Earth. Some of the universe's earliest galaxies owe their discovery to this gravitational trickery. The black hole at the heart of galaxy cluster MAX J0647 plus 715 acts as a natural telescope, magnifying a galaxy from when the universe was just 500 million years old, a time when the first stars were still flickering to life. Without this cosmic lens, the galaxy would be far too faint for even our most powerful telescopes. Black holes, often seen as destroyers, become unlikely enablers of discovery, bending light to illuminate the universe's darkest corners. As our instruments grow sharper, these gravitational lenses are revealing even wilder phenomena. Some warped images show the same supernova exploding multiple times, its light taking different paths around the black hole and arriving years apart. Others hint at intermediate mass black holes, long sought missing links in black hole evolution lurking in lensed galaxies. Every distorted ring or stretched arc is a cipher waiting to be decoded, a message from the universe written in the language of warped spacetime. And with next-generation telescopes like the Vera Rubin Observatory coming online, we're on the verge of finding thousands more of these cosmic mirages, each one a window into the universe's most elusive secrets. Black holes might be the universe's most mysterious objects, but when it comes to their essential properties, they're surprisingly boring. That's the bizarre implication of the no-hair theorem, a cornerstone of black hole physics stating these cosmic monsters can be completely described by just 3 traits: mass, spin, and electric charge. Every other detail, what they swallowed, where it came from, even the atomic structure of stars they've shredded gets erased beyond recovery. The name no hair isn't about literal grooming habits, it's a metaphor for simplicity. Just as a bald head lacks individual strands, black holes lack distinguishing features beyond those three numbers. It's as if the universe took a cosmic blender to all the complexity that ever crossed the event horizon, leaving behind only the blandest possible summary. Think of it like trying to identify a person solely by their height, weight, and whether they're left or right-handed. You'd miss everything that makes them unique, their memories, personality, even the color of their eyes. That's the frustration astrophysicists face. Two black holes with identical mass, spin, and charge are indistinguishable, even if one formed from a collapsed star and the other devoured an entire solar system. This radical simplicity arises from how black holes obliterate information. When matter falls in, the event horizon smears it into a featureless slurry, like hitting the reset button on a hard drive. The only traces left are those three imprinted numbers carved into space-time itself by the black hole's gravity. Why does this matter? The no-hair theorem places hard limits on what we can ever learn about black holes. No matter how advanced our telescopes become, we'll never reconstruct the history of what fell in. It also creates a paradox. If black holes truly erase information, they violate quantum mechanics' sacred rule that information must be preserved. This contradiction sparked decades of debate, leading to breakthroughs like Hawking radiation and holographic theory, ideas pushing physics to its absolute limits. The theorem isn't just a quirky fact, it's a flashing neon sign pointing toward gaps in our understanding of reality. Yet there might be loopholes. Some theories suggest quantum hair could exist, subtle imprints left on a black hole's gravitational field by what it consumed. Others propose that information isn't destroyed but encoded in ways we can't yet decode, like a cosmic QR code scrambled across the event horizon. Future gravitational wave detectors might spot deviations from the no-hair theorem's predictions, revealing hidden complexities beneath the surface. For now, black holes remain the universe's ultimate enforcers of minimalism, proving that sometimes the most terrifying things in existence are also the simplest. Imagine approaching what you think is a calm lake, only to slam into an invisible wall of fire the moment you try to enter. That's the unsettling premise behind the black hole firewall theory, a radical idea suggesting event horizons aren't the smooth gateways Einstein predicted, but searing barriers that would vaporize anything crossing them. At first glance, it sounds like science fiction, but this concept emerged from one of physics' most heated debates, the black hole information paradox. If quantum mechanics insists information can never be truly destroyed, how do we reconcile that with black holes seemingly erasing whatever falls in? The firewall proposal offers a violent solution by torching incoming matter at the horizon. The black hole converts it into radiation that preserves information. It's like a cosmic shredder that somehow keeps perfect records of everything it destroys. The implications are staggering. Traditional relativity paints the event horizon as an unremarkable boundary, a point where gravity becomes inescapable, but where no dramatic changes occur locally. An astronaut crossing it wouldn't feel anything unusual until tidal forces eventually pulled them apart. Firewalls shatter this picture. If they exist, the horizon becomes a sudden death zone where matter gets flash-fried into Hawking radiation, resolving the information paradox by ensuring data gets scrambled outward rather than vanishing. But here's the catch. This violates Einstein's equivalence principle, which states that free-falling observers shouldn't detect extreme physics at the horizon. It's like saying you'd spontaneously combust the moment you stepped into an elevator in free fall, a clear contradiction of everyday experience scaled up to cosmic extremes. Critics argue firewalls create more problems than they solve. If horizons are lethal, what happens to the black holes we've observed merging? Their event horizons would have annihilated each other upon contact, releasing unimaginable energy, yet LIGO gravitational wave detections show smooth mergers consistent with classical relativity. Others point out that firewalls might require rewriting not just relativity, but quantum field theory itself. The debate has spawned alternative solutions, from fuzzballs in string theory where the horizon is a tangled quantum mess, to holographic models where information gets encoded on the surface like a cosmic DVD. Yet the firewall idea refuses to die because it highlights a genuine crisis in physics. At the heart of the controversy is a deeper question. Do we need to sacrifice Einstein's vision to save quantum mechanics, or is there a third path waiting to be discovered? Future gravitational wave observations might hold clues. Subtle echoes in merger signals could betray firewalls' presence, or their absence could force physicists back to the drawing board. For now, these hypothetical infernos remind us that at the boundaries of known physics, even the simplest assumptions like the nature of a black hole's edge can ignite revolutions. TUN 618 doesn't just consume matter. It devours entire stars' worth of material every single day to fuel its blinding luminosity. To maintain an accretion disk that outshines thousands of galaxies combined, this cosmic behemoth must gorge itself at a rate that defies earthly scales. Calculations reveal it swallows roughly one solar mass, the equivalent of our sun, every 10 days. But let's break that down into terms that truly stun the imagination. That's like ingesting 400 Earths daily, or a mass equal to Mount Everest every second. Picture our entire planet vanishing into its maw in less than 22 minutes, reduced to superheated plasma before crossing the event horizon. To grasp the sheer volume, imagine our solar system's largest gas giant, Jupiter. TUN 618 consumes a Jupiter-sized mass every 3 days, turning what we consider a planetary giant into mere cosmic appetizers. Even more staggering, if you combined every asteroid in the main belt, every moon in our solar system, and even the rings of Saturn, you'd still only have enough material to feed this black hole for about 6 hours. Its hunger is so relentless that the energy released from this daily feast equals the total output of a hypernova, a star's catastrophic explosion repeated every few moments. But here's the twist: this consumption isn't steady. Like a campfire fed by gusts of wind, TUN 618's intake fluctuates based on the density of gas and stars swirling around it. During active feeding periods, it might gulp down 2 solar masses a week, while quieter phases see it snacking at half that rate. These variations create flickers in its luminosity, cosmic heartbeat echoes visible across billions of light years. What's truly unsettling is that despite this monstrous diet, TUN 618's event horizon is so vast that the infalling matter spreads thin, like a raindrop falling into an ocean. The violence happens silently, invisibly, with no dramatic crunch or splash, just the steady glow of a universe's worth of material being unmade, one star at a time. Hidden in the flickering X-rays from feeding black holes lies a cosmic secret, ghostly echoes that reveal more about these dark monsters than we ever imagined. NASA Neutron Star Interior Composition Explorer, or NICER, an instrument aboard the International Space Station, has been catching these whispers from black holes like a celestial eavesdropper. Picture a black hole's accretion disk as a swirling storm of superheated gas, where particles collide at near light speed, emitting X-rays like a strobe light in the cosmic dark. But sometimes those X-rays don't reach us directly. They bounce off nearby clouds of gas and dust, creating faint, delayed copies of the original signal echoes that arrive milliseconds to seconds later, like light reflecting off a cave wall. These echoes aren't just random noise, they're treasure maps. By analyzing the time delay between the primary X-ray burst and its echoes, astronomers can triangulate the distance between the black hole and the surrounding gas structures. It's akin to sonar in the ocean. Send out a pulse, listen for the rebound, and suddenly the invisible becomes measurable. NICER observations of the black hole system XTJ 1859 plus 226 revealed echoes mapping gas as close as 20,000 miles from the event horizon, a stone's throw in cosmic terms. At that range, gravity warps spacetime so severely that the echoes carry distortions betraying the black hole's spin, mass, and even how its magnetic fields churn the nearby plasma. The real breakthrough came when scientists realized these echoes change based on what the black hole is eating. During hard states, when the disk emits high-energy X-rays, echoes suggest the inner disk evaporates into a hot corona of particles, while soft states show the disk extending nearly to the event horizon. This flip-flopping behavior solves a long-standing mystery: why some black holes flicker unpredictably. The echoes prove it's not random chaos but a precise interplay between the disk structure and the black hole's feeding rhythm. But the most stunning implication lies beyond single black holes. Echoes from supermassive black holes like those studied by the European Space Agency's XMM Newton telescope show gas clouds hundreds of light-years away still carrying these imprints. That means a black hole's influence isn't confined to its immediate vicinity. It etches its presence across galactic scales, with echoes acting like breadcrumbs leading us through its gravitational labyrinth. Future missions promise to decode even fainter echoes, potentially revealing the hidden structures that guide matter toward oblivion, and proving that even in the darkest corners of space, nothing goes unnoticed. One of the most provocative ideas in modern cosmology suggests black holes might be hiding the key to dark energy, the mysterious force accelerating the universe's expansion. This radical theory, bolstered by a groundbreaking 2023 study, proposes that the growth of supermassive black holes could be intrinsically linked to the cosmos's outward rush. It's a concept that turns conventional wisdom on its head. Instead of merely responding to the universe's expansion, black holes might actively fuel it, their insatiable appetite somehow translating into the energy stretching space itself apart. At the heart of this idea lies a startling observation. When astronomers compared ancient black holes from the early universe to their modern counterparts, they found the latter are consistently 7 to 20 times more massive than expected, even accounting for mergers and accretion. This discrepancy aligns eerily with the timeline of dark energy's dominance, which began roughly 5 billion years ago. The correlation sparked a daring hypothesis. What if black holes aren't just growing within an expanding universe, but are themselves sources of dark energy? The mechanics behind this proposal delve into quantum weirdness. Within a black hole's core, general relativity predicts a singularity, a point where density becomes infinite and spacetime breaks down. But some theorists suggest these singularities might be gateways to vacuum energy, the same theoretical background energy permeating empty space that could drive cosmic acceleration. As black holes consume matter, their interiors might store this energy in distorted spacetime regions, effectively coupling their growth to the universe's expansion. It's like imagining each black hole as a cosmic battery, charging itself by eating stars and galaxies, then discharging that energy into the fabric of reality itself. The 2023 study added striking evidence. By modeling black hole mergers across cosmic history, researchers found their combined mass after collision often exceeds the sum of their parts, an anomaly that could be explained by the creation of new vacuum energy during the merger process. This energy wouldn't just vanish, it could seep into the universe as dark energy, subtly pushing galaxies apart. The math is tentative, but the implications are staggering. Supermassive black holes might be cosmic engines converting matter into the very force tearing the universe asunder. Skeptics highlight glaring questions. If black holes truly generate dark energy, why doesn't their contribution overwhelm other cosmic structures? And how does this square with observations showing dark energy's uniform distribution? Defenders counter that the effect could be cumulative, with trillions of black holes across the universe collectively driving expansion without local disruptions. Others propose modified gravity theories where black holes naturally screen dark energy's effects in their vicinity, masking their role until viewed on cosmological scales. Whether this theory holds or collapses under scrutiny, it underscores a profound shift in how we view black holes. No longer just gravitational endpoints, they're emerging as dynamic players in the universe's grand narrative actors capable of shaping not just galaxies, but the fate of spacetime itself. Future gravitational wave detectors and next-gen telescopes could settle the debate, hunting for telltale signatures in black hole mergers or probing the subtle interplay between cosmic voids and supermassive black holes. Until then, this tantalizing link between the darkest objects and the universe's most elusive energy remains one of science's boldest puzzles, a reminder that even our most fundamental assumptions about reality might be rewritten by the cosmos's deepest shadows. Imagine an advanced civilization that didn't just survive near a black hole, they thrived by turning this cosmic monster into their ultimate power source. These hypothetical beings would live on a planet orbiting at just the right distance, where time dilation slows their clocks relative to the rest of the universe, while the black hole's immense gravity provides unlimited energy. They might construct a Dyson sphere-like megastructure called a Penrose sphere, capturing energy from the black hole's accretion disk or even tapping into its spin through quantum effects. Every second for them could mean years passing elsewhere, turning their world into both a time machine and an energy oasis. But survival here would require staggering technological mastery. Tidal forces could rip apart planets that orbit too close, so their home would need to be either artificially stabilized or built on a massive engineered habitat. The black hole's intense radiation would demand shields far beyond anything we've conceived, while their entire infrastructure would have to account for spacetime's extreme curvature. Even communication with other civilizations would become a challenge. Messages sent from their world might arrive centuries later elsewhere, forcing them to develop entirely new forms of diplomacy and trade. The social implications are even wilder. Time dilation could split their society into castes, those living closer to the black hole aging slower than those farther out. Generations might pass in the outer colonies while a single lifetime unfolds near the event horizon. Their art, philosophy, and even language would likely revolve around temporal relativity, with concepts like now becoming fluid and subjective. Some theorists suggest such a civilization might view time like a landscape, traversing eras as easily as we cross continents. Could humanity ever reach this level? The challenges are immense, but the rewards might justify the risk. A single supermassive black hole could provide more energy than all the stars in a galaxy combined, making it the ultimate solution for a civilization facing entropy's inevitability. And if we ever master the physics needed to survive there, we'd unlock the universe's deepest secrets, turning the cosmos' most destructive force into our greatest ally. Remember the haunting B-flat humming from the Perseus black hole? Now picture that same cosmic music, but scaled up to match Ton 618's unimaginable proportions. If this 66 billion solar mass titan could sing, its voice wouldn't just echo through its galaxy, it would vibrate the fabric of the universe itself. Whereas Perseus's sound waves ripple every 16 million years, Ton 618's hypothetical frequencies would stretch across epochs, with each oscillation lasting longer than the current age of our cosmos. The physics behind this is staggering. A black hole's pitch depends on its mass. The larger the hole, the deeper the tone. Perseus's hum registers 57 octaves below middle C, but Ton 618 would plunge into infrasound so profound it makes seismic waves seem like piccolos in comparison. Calculations suggest its dominant frequency would cycle once every 390 trillion years, a time span so vast it dwarfs the universe's 13.8 billion year existence by a factor of 28,000. This isn't just sound slowed down, it's the universe's deepest bass note stretched beyond the limits of time as we know it. Why can't we hear this cosmic symphony? The answer lies in scale. Human ears detect vibrations between 20 and 20,000 cycles per second. Ton 618's oscillations are so lethargic that translating them into audible sound would require compressing trillions of years into mere seconds, like trying to listen to continental drift by speeding up geological time a quadrillion-fold. Even if we could, the frequency would be so low it would register as a single, unchanging pressure wave rather than discernible sound. Yet this silence speaks volumes. The absence of detectable sound from such giants reveals a fundamental truth about supermassive black holes. Their interactions with surrounding gas occur on scales too vast for pressure waves to form in ways we'd recognize as sound. Where Perseus's bubbles create vibrations in dense cluster gas, Ton 618's environment is too diffuse, its gravitational influence too overwhelming for rhythmic pressure changes to propagate. Its voice isn't muffled, it's written in a language of space-time curvature and tidal forces rather than air compression. Future observatories might uncover subtler traces of this cosmic resonance. Just as seismometers detect earthquakes too faint for humans to feel, next-generation gravitational wave detectors could potentially identify ultra-low-frequency vibrations from colliding supermassive black holes, events where Ton 618-sized giants warp spacetime itself like drumheads. These wouldn't be sounds as we know them, but mathematical rhythms encoded in the stretching and squeezing of the cosmos, waiting for instruments sensitive enough to translate gravity's ghostly whispers into something we can finally comprehend. From the incomprehensible scale of Ton 618, a black hole so massive it could swallow our solar system without blinking, to the way these cosmic titans sculpt entire galaxies with their gravitational might, we've journeyed through some of the universe's most mind-bending realities. Who could forget that supermassive black holes aren't just destroyers but cosmic recyclers, spitting out the very elements that make life possible? Or the chilling revelation that time itself warps near their event horizons, where minutes stretch into millennia for distant observers. These invisible giants defy logic at every turn, whether it's their ability to sing in frequencies lower than human comprehension or the possibility that their growth might be fueling the universe's accelerating expansion. Yet for all we've uncovered, the most thrilling thought is how much remains hidden. What other secrets lurk in the darkness between those flickering accretion disks? Could black holes truly be gateways to other dimensions, or the key to unifying physics' greatest theories? The universe keeps its cards close, but every new telescope, every gravitational wave detection, peels back another layer of the mystery. Before you go, let us know which fact left you utterly stunned. Was it the black hole spinning at nearly light speed, or the way these cosmic monsters might outlast everything else in the universe? Drop your favorite revelation in the comments, and if your brain hasn't completely melted from all this cosmic wonder, hit like and subscribe for more journeys to the edge of reality. After all, the universe's greatest stories are still being written, and who knows what we'll discover.